Washington State University. Go Cougs!
Hello everyone. In this video, I'm going to cover lesson 4 of Python for Data Analytics, where we're going to continue our discussion of NumPy ND arrays from our previous lesson. Since this is a new Jupyter Notebook, I'm going to need to re-import NumPy as NP. Now we're going to discuss vectorization, which is a very powerful topic of ND arrays and NumPy. So let's motivate vectorization with an example. Say I have two Python lists. The first Python list is going to be 10 numbers 1 through 10. The second one will be 10 numbers of all 10s. And I want to have a result of adding each element in X to each element in Y. And I want to store this in a list called Z. So to do this, I'm going to have to write a loop. For I in range X, I'm going to go ahead and append to the end of Z X sub I plus Y sub I. And then I can go ahead and print out the result, and we'll see 1 plus 10 is 11, 2 plus 10 is 12, and so on and so forth. Now, we wouldn't have to write this loop if the addition operator was overloaded such that it knew to add element-wise each item in X and Y. That is exactly what vectorization does for ND arrays. Essentially, we're going to express batch operations on data without writing any loops. So let's see this same example, but using ND arrays and overloaded addition. So X this time is going to be np.arange, and we'll do the same range of values so we can check our results. So Z is going to be assigned simply X plus Y, and I go ahead and print out Z, and there's our same result, but we didn't have to write a loop. Now, there are many operations that are vectorized in NumPy. Addition is just a really great, straightforward example to get us started. Now, whenever we talk about vectorization, it's also useful to talk about broadcasting. So broadcasting is essentially a form of vectorization that occurs when the two ND arrays are not of the same shape. For example, let's suppose we have np.arange, we'll do 10 again, and we have a vectorized multiplication operator that's going to multiply each item in X by the ND array that only contains a single item, which is the item 2. So obviously this first ND array X has 10 items, but the second ND array here has only one item in it, and that is element 2. So these are two different length ND arrays, and what's going to happen is this value 2 is going to be broadcast to every single item in X. So essentially, we're just going to multiply every item in X by 2. And if I print this out, that is exactly what we see. So for example, 1 becomes 2, 9 becomes 18. Now, the next thing I want to show you relates to our previous lesson where we were replacing every negative value in a random ND array with zeros. So essentially what we were doing when we were testing for a value less than 0 is we were applying a vectorized less than operation. So a less than operation is an example of a relational operation where we have relational operators such as equal, not equal, less than, or greater than, etc. So let's dive into this in more detail so that we can more fully understand vectorization and what we saw happen in the code in our last lesson. So here I have two ND arrays, M names and M ages. Each one of these is 6 items long. So M names has 6 strings, Mary, Michael, Margaret, Mary, Marcus, and Molly. We see we have 2 repeated Marys. M ages is a ND array of integers, 28, 72, 12, 34, 40, 68. Now, these are intended to be parallel arrays, meaning the item at position 0 in M names is associated with the item at position 0 in M ages. So this Mary is 28 years old, Margaret is 12 years old, and this Mary is 34 years old. So let's create a Boolean array where we're going to find out where the Marys are in M names. So Marys is going to be assigned M names equal to Mary. So we run this and we get true, false, false, true, false, false. So true, false, false, true, false, false, which is as we would expect. So now, let's say we only want to get the ages for the Marys. So let's index into M ages with Marys. And now we've only selected 28 and 34, which is the age of the Marys. So this is an example of vectorized equality here, and an example of alternative indexing where we're indexing using a Boolean array. Let's do one more example where we're looking at vectorization and Boolean arrays. We also have support for logical operators and or not. These are the keywords used in Python for these operators, but in NumPy, these are going to be ampersand for vectorized and logical and the pipe for logical or. So here we have our M names and M ages again, and this time, instead of only getting the Marys, let's get the Marys and the Marcuses. So we want to have a logical OR operation here so we can get the Marys or the Marcuses. So let's do the same as before, M names equal Mary, and we'll do M names equal Marcus. So if either item, or if any item in M names is Mary or Marcus, then we're going to get a true. Otherwise, we'll get a false. So now, our second to last item here went from false to true because now we're also accepting Marcuses as well. And let's try our M ages code again to select the ages for the Marys and the Marcuses, and we'll see there's one more entry added there, which is 40, which is the age of Marcus. A few more topics to cover include reshaping, transposing, and working with universal functions. So for reshaping, we could change the shape of an ND array object by using reshape. So let's start with our X again. X is np.arange10, so 0 through 9. And let's print out the shape of X, and we'll print out X as well. So there's our ND array. It's one-dimensional of 10 items. Okay, so now let's reshape this data so that instead of a one-dimensional array, it's going to be two-dimensional, and it's going to be 5 by 2. So now I run this. Here's our shape, 5 by 2. So this linear data is restructured into 5 rows of 2 columns. Next topic to cover is transposing. So let's take an example where we have, let's say, 6 values, 0 through 5, and let's reshape it into a 2 by 3 matrix or 2 by 3 ND array. And let's print out X, let's print out the shape of X, and now let's take the transpose of X, which is going to turn the rows into columns and the columns into rows. So we can get that with .t, and let's print it out and print out X sub t dot shape. So run this, and here we have our 2 by 3, and it's converted to a 3 by 2. So for example, 0, 3 column became 0, 3 row. Last topic for ND arrays, and then everything else we need to know about ND arrays, NumPy, SciPy, we will learn on the fly. So ND array has several fast vectorized universal functions, also called ufuncs, that perform element-wise operations on data. So we can take a look at two different types of ufuncs, unary and binary. So unary ufuncs operate on a single ND array. So sticking with our example, X is np.arange, print out X, and then let's print out the square root of X, but element-wise. So this is going to return the same length or same dimensional array as X, but where each item is the square root of the item at position I, for example. Another example, let's do x2 gets np.random.randn. Let's do a square matrix 4 by 4, print x2, and let's print out the absolute value of every element in x2. So before, for example, negative 1.49 changes to 1.49. Now let's take a look at binary ufuncs. So these are universal functions that accept two ND arrays, apply an operation element-wise, and return a single array as a result. Let's take a look at two example binary ufuncs, power and max. So let's get some data. So X is np.arange. Let's just do 5 this time, just to work with fewer numbers. Let's have powers be np.full. Let's have 5 2s. So essentially what I'm trying to set up here is raising X to the power specified in powers element-wise. So right now this is just going to square every element in X because powers is all 2s. Can I see that? That looks right. 4 squared is 16. Okay, awesome. Now, if I didn't want to specify powers, I could just specify 2, and this would broadcast 2 to each item in X because this is not the same length as X. So there's an example of broadcasting. And let's just say for fun, maybe I change powers sub 4, that'd be the last one, to 3. So we're going to cube 4 instead of square it. And there we see 4 cubed is 64. So the next example let's look at is maximum. So let's create another ND array. Let's do the same as X, but let's add 1. And now let's print out np.maximum of X and X2. So essentially what this is going to do is it's going to grab the largest element, element-wise, to construct the returned ND array. So right now, since I added 1 to each value, essentially in an ND array that was equivalent to X, it's going to be equal to X2. But let's say I actually set, let's do x sub 3 to 100. Then this is going to grab the 100 at index position 3 from x because it is going to be larger than the value at index position 3 in x2.